Okay, great. Sorry for the delay. So let's see. Uh, on the PTE side, uh, I have a few more spots. So if any of you are waiting, I'm going to be sending out a little poll. I still have to figure out what's the fair way of doing it. Some of you are saying you are second year students. Unfortunately, I will not be teaching this course the following year. I'm going to leave. So whether you are first year or second year, in my eyes, you are equal. So, and also roughly half the MS students take CES. So just because you are in CES doesn't really make it something that I can let you in. So I have to figure out, probably the fairest thing would be just the waiting list order, but I realize that has its own unfairness because UCLA opens the enrollment in waves. So the luck of your last name or first name affects it also.
A quick question. The slides will be available on
They're already there.
okay, perfect.
Yeah. Slides, the recording of the first lecture. If you just go to the resources tab and the lectures, you'll see everything. Okay. If you have problem accessing anything, let me know. I don't know. Did anyone try accessing the slides? You can. Okay. Great. I really wish there was something higher about here. Anyways, so last time towards the end, I was kind of talking about that there are many different ways that you can implement the computational core of an embedded platform. And essentially, you can think of it in terms of the degree of specialization that you do. And kind of in some obvious manner, you can say that for speed and power, the more you are able to specialize, hopefully you'll do better. But cost is one of those things where, depending upon whether you are making one unit of some, or a few units of something versus lots of units of something, that affects things because your cost has both kind of a recurring component and an upfront design component. So basically, when you use something like a microprocessor or a microcontroller or a FPGA, then you are sharing the design cost and sort of manufacturing setup costs like masks for chips and all among potentially millions of users, millions of devices. Whereas if on the other hand, you're making an ASIC, then it's just your product. So when it comes to therefore, so when it comes to the cost structure, it sort of cost depends upon your volume. That's kind of the main point. If you so within like our department, EC department, for example, you'll see the professors who make specialized chips because they're creating things which have such extreme requirements in terms of performance or where they are being placed, that that kind of dictates things. So like, for example, work on like brain interfaces, for example, right? I mean, this is not something where you're going to put Intel microprocessor or on microprocessor. On the other hand, then there are people who are really creating one-off systems, and it could be done. The performance requirements are such that you can do it through a variety along that spectrum, and then in that case, often time to design and cost begins to dominate. So micro tends to be there. We usually customize at the level of making a board, but not making our own chip, for example. So yeah, depends on what you are kind of doing. One other thing is that these things are intrinsically tied with the economics of what you are doing. I mean, not just the cost, but also delay in your product really translates into increasing the cost because if capital is tied up. Yield, right? What percentage of your devices are working out, coming out correctly? The whole infrastructure around it in terms of debugging, testing, all those kind of things. So there's a complicated story which is hard to say. Now, the most common embedded systems that you will find are basically tend to make use of some sort of a processor. And within that, The most dominant type of processors are the so-called microcontrollers or MCU. And you can think of microcontrollers as essentially putting a whole computer onto a chip. They're integrating CPU, or what is also referred to as the processor core, but then they'll also have the program memory and the data memory with the stack and the working your data structures go. They're all sitting onto the same chip, and then also peripherals. So unlike your bigger computers where sort of microprocessor is a standalone chip and then memory and peripherals are elsewhere on the motherboard, microcontrollers kind of integrate all these things. And then there are versions of these which are specialized according to how much memory, how much, what kind of peripherals, and so on and so forth. So majority of the processor cores that exist, in the sense that if you think in terms of how many processors are being made across the world, then most of them are in the form of these microcontrollers. And these microcontrollers used to be pretty puny. I mean, if you go back to like 1980s and all, or even 70s, there were these 4-bit, 8-bit type things which dominated, but they were not terribly interesting. But then, if you look now, the kind of stuff that you have available are pretty powerful. They are multiple cores. They are not all that different from your laptop processors and all of just a few years ago. And in many ways, like, I mean, if you look at the processor and the cutting edge stuff, like, let's say a smartphone or some of the Raspberry Pi type boards and all, they're not all that far off from what you would find in laptops or even desktops just a short time in the past. So these MCUs, because they integrate everything, literally you can think of them as a software programmable hardware, right? I mean, you can put the program there, your program runtime stuff resides there, the peripherals are there. In some cases, there are even tiny little FPGAs and all on it. So you literally can implement in software was hardware building blocks, right? So you can use it for some super simple stuff, but they shine when you're doing some more complicated logic, something which has a lot of temporal, as well as sometimes they have. Okay, so so the difference between microprocessor and microcontroller simply is in terms of the level of integration, and kind of the set of companies which are active in these marketplaces are different. Intel, AMD, these kind of companies tend to be in the microprocessor regime, and then companies which kind of make these microcontrollers are setups like STM and Nordic and all, which in turn purchase the processor core from companies like ARM, and increase India mentioned RISC-V, and sometimes the companies like TI and all with their own processor cores, and then they make these microcontrollers. So it's just the level of integration. Beyond MCUs, beyond microcontrollers, there are other more boutique forms of computational units. So sometimes they put, in addition to a processor core, they would put some hardware which could be configured. So it's almost like, in addition to software stuff, you also have hardware which you can wire using appropriately programming, doing the wiring, but doing the wiring in software. So FPGAs are a great example of it, but there are other variants of this. Common to all of them is some sort of logic building blocks which you wire up. So some companies make chips which have both these components. So firstly, the big FPGA companies like Xilinx have FPGAs which have hard processor cores. That is, there is a part of the chip where you actually just have a processor sitting, and the idea is that now you can make a whole system where you have a processor and you have the glue logic and accelerators and things like that you can kind of surround it. At the low end, there are companies like Cypress who kind of do the same thing, and sometimes they even have analog components. So literally kind of everything that you might imagine in a system just sits on a single piece of silicon and then works off. Nowadays, so a challenge when you integrate all these things is that it's kind of like jack of all trades. So it's very hard. So if you think about like how is memory made, DRAMs use special processes, right? semiconductor processes are different. If you're making an analog component, again, it has different requirements. But if you're trying to put everything on the same silicon, then the challenge you face is that you have to compromise, right? Either digital part would be non-cutting edge, or analog design becomes more challenging, or not. So what has happened now, as in like recent years, is this concept called chiplet. Okay, and actually UCLA is pretty active in that. But kind of the idea is that you take little chips, pieces of silicon die for these different things. You get the best processor and the best radio and whatnot, and then you slap them on a bigger silicon substrate and then wire them together. So it's almost like a hierarchical chip. You can think of it like that. So the name is chiplets, but little die. They literally, like, these are no longer packaged chips. They're just bare silicon die. You slap them on a bigger substrate, usually another piece of silicon, for example, and then wire them up. And so companies like Apple, for example, for the bigger processors are kind of using that because they can put memory and processors in the same way. But the use of this is a lot wider in the sense that you can integrate all sort of stuff, radios and optical stuff and all on these bigger substrates.
Could you quickly explain the idea, like why chiplets might be preferred over to maybe just like buying the IP, the RTL, like IP, and putting them all on something?
Sure.
Yeah.
Like so I think I failed to make that point convincingly. So if you purchase IP blocks, right, the designs, and put them all on the same silicon, the issue still is what semiconductor process do you use? And the semiconductor process which is best optimized for memory may be different than for your radio, may be different than for the processor. So you have to compromise, right? And whereas chiplet approach basically lets you use the best. So there's a lot of emphasis on that, and I'm sure some of you may have read about this big CHIPS initiative that US federal government has started, right? Some $250 billion that they're giving out to companies and universities and all. One of the big part of that is to create a whole chiplet ecosystem, right? So almost like if you roll back to 60s, 70s, 80s, early days of electronics, we had like bins of chips and we'll make PCBs. That's how the electronic industry started. Now we are headed into bins of these dies, and you can very rapidly connect them on a substrate and get near chip-like performance, but a lot of flexibility. So there are already some startups and all where you can go and kind of configure your chip using these chiplets, and they take care of the fabrication part.
Are chiplet systems noticeably bigger than sort of the more fully integrated blocks?
They are bigger, of course, but not that much more. Yeah, they're pretty fine. I think Professor Puneet Gupta is teaching 201A. I don't know if any of you are taking it, but he may be talking about that. He is one of the experts in chiplets, for example. So yeah. So some of the papers that have emerged, including from his group and all, have shown that you can. So while you do lose somewhat in the scale, but you gain so much more in your ability to integrate in the same volume overall, because you're eliminating layers of packaging that sort of come out ahead. And actually, big part of like Apple's M1 and 2 processors have done so well is because they were the first large-scale exploitation of the chiplet technology. So chiplet started out just a few years ago, and now you're beginning to see it penetrate all sort of products. Okay, and as we kind of integrate things into whatever inside brain and wearables and stuff like that become much tinier, it's just going to scale and the economics will become better. Okay, so what else? Yeah, this is another example of an FPGA which has programmability and all. Okay, so one of the things that distinguishes microcontroller from regular processors is just the sheer diversity, right? I mean, because we also are integrating memory and sensor peripherals onto it, and yet like different applications tend to have specific needs. Like if an automobile company needs something for cars, they probably need some interfaces which are meant for cars. So whenever you go to these winters, there's a big diversity of microcontrollers available, and moreover, there are big diversity of vendors available. So I've sort of shown sort of architectural diversity, vendor diversity, and within each vendor, lots of things. In fact, these puny little MCUs were behind the well-advertised supply chain problem that hit the car industry. Okay, they call it ECUs, electronic control, engine control unit or something like that. But these are nothing but little MCUs. Okay, and these things sell for like a few dollars. Tesla reportedly designed their systems so that they could work across different microcontroller families, and therefore they were less hit, at least that's what the news said, whereas some other companies which were deeply wedded to a particular supplier had bigger hits in this process. Okay, so yeah, so this just shows like one vendor, ST, one of the bigger and more famous one is just like if you go to their website, like they would have things optimized for speed, things optimized for memory, things optimized for power, kind of all kind of things and all. Okay, so like literally tens and tens and tens of devices, all using, like in case of ST, they are heavy users of ARM processor cores. So at some level they are all the same, that is same instruction set architecture, but yet tremendous amount of diversity catering to different markets, and since each market is pretty big, they can afford to have this differentiation. Okay, yeah. So emerging microcontrollers, so I mentioned last time also RISC-V. So Berkeley was kind of, at least on the academic side, was the one which brought out RISC architectures back in early 80s, and RISC originally came from IBM, but Berkeley was the one which sort of really amplified it. And then in recent years, I guess the philosophy was software had open source, but there was nothing counterpart on the hardware side. It was locked up behind proprietary processor architectures, Intel, ARM, so on and so forth. So pretty much the same, like the CS department in Berkeley, they kind of started this effort called RISC-V, 5th generation RISC, and they released a bunch of open source designs, and a lot of setups picked it up and all, so it has become extremely widely adopted. It's now like there's an international foundation, there are conferences around it and stuff like that. Main point is that people have shown, so what Berkeley did is define the instruction set architecture. So if you think about processor, right, if you've done a computer architecture course, they always talk about, like, right, there is the instruction set architecture, essentially the set of assembly instructions, and there is implementation. I can take the same ISA and I can have many different implementations of it, right? Some implementations may have different cache sizes, maybe different level of pipelining, right? I mean, they may differ at the microarchitecture level, but they all execute the same program, program in the same instruction set architecture. So RISC-V is the same thing. There's an instruction set architecture, well, a few versions of it now as they evolve. And then there are many, many different implementations of it, ranging from tiny microcontrollers, those suited for like low power applications, to those which are kind of even aiming for server class stuff. So this is a new sort of entity which is really shaking things up for a variety of reasons. Right, I mean, one is if you use ARM processors. So ARM was not very friendly with academics, barring a few exceptions. So if you wanted to work with ARM processors, it was pretty hard because you maybe you will get a closed design, but you couldn't really modify it. Whereas RISC, you could do all the modifications, add a new instruction, play with it. So that was one. So universities obviously loved it. Then the second thing is that when you use an ARM processor as a company, there are two different models, right? One is you can buy a processor core design and then just plop it onto your chip. That's the IP model. But then there are few entities which license the architecture, and then they create their own implementations of that architecture, right? So they go with their own microarchitecture. Only very big companies are able to do it. Apple, Qualcomm, Samsung, these kind of companies, right? And even in their cases, creating a new implementation is not easy, and probably, I mean, if you look at newer versions of like Snapdragon, for example, a lot of times they're just using standard ARM parts. Apple is probably the one which has pushed sort of the ARM architecture on its own quite a bit. So as you can gather, I mean, it takes trillion-dollar companies or hundreds of billion-dollar companies to be successful at that. So RISC-V, the advantage is that it's open source, so you don't need to pay an arm and a leg to sort of get the architecture license and all. So there are a lot of rumors going on, like Intel attempted to buy Sci5, which is the big, most prominent startup in the space. Rumors about Qualcomm going with RISC-V. There are all sort of these things keep floating around. There's a geopolitical angle, which I mentioned, right? ARM embargo on it, so China is favoring their own homegrown processors and RISC-V quite a bit. So there is a complicated economic, political, technical sort of set of arguments because of which RISC-V has a lot of wind behind it. Okay, so when you are picking something like your MCU, which you make, it's not like one metric that you have to consider. There are a whole bunch of things that you'll have to take into account. So if you look at speed, you'll find that there are things which run at kilohertz, which are designed for like super low end or very low power, perhaps being implanted. You need like picowatts of power consumption kind of things, stuff which are running at a few gigahertz, huge range. Then power, actually I should probably say, like commercially you can buy stuff which is maybe nanowatts to watts in the active mode, and sleep mode sort of picowatts to microwatts. Program memory, this is where microcontrollers, because you're integrating everything onto the same chip, your unique program memory has to be persistent, so commonly we use flash, and you're probably going to have like a few meg at most. So you are suddenly in a realm where much, like if you think Linux is efficient relative to Windows and all, how big is a Linux kernel? Anyone? Maybe combine, maybe like install Linux and never notice how big the kernel is. Right? So go sometime look at it, right? Linux kernel itself is tens of megabytes, right? So clearly, if you are talking about things which are single-digit meg or even sub-megabyte, you can't just do computing in a normal way. So at the low end, they are really just kilobytes, and at the high end, maybe you will hit a gigabyte. Okay, like if you are into Raspberry Pi class stuff and all, you may have an external DRAM, but if your memory is on chip, you'll be megabytes. Data memory, this is where you stack and dynamic data structures go and all, and these are even tinier. In some cases, they're like tens of bytes, in other cases, maybe a small number of kilobytes, and you're trying to run operating system and neural network nowadays and all sort of stuff. So pretty challenging. I/O, this is where they excel. They have tons of I/O. Normal microprocessor will give you a address and data bus, and then you hook things externally. Whereas here, there are all sort of specialized I/Os that exist, including analog stuff and all as well. Peripherals, all sort of timers, counters, stuff like that, variety of internal things, and then sort of course, if you're making these things and all, then the whole ecosystem of tools and all is very important. The way you develop software with microcontrollers is not quite the same as the way you develop for your laptop servers and all. So, so those are all considerations. So a typical MCU-based embedded platform, which basically is the most common form of embedded platforms, would have some sort of an MCU or MCUs, possibly with multiple cores. Oftentimes they come with radios on board, so you may have Wi-Fi or Bluetooth or Z-Wave or Zigbee or bunch of such things, options there. Of course, RAM and flash and stuff like that, and then variety of sort of interfaces and all. So the one which I've used in recent years in the class is this Arduino device called Nano 33 BLE Sense. BLE stands for Bluetooth Low Energy. 33, I don't know what 33 stands for. Nano, tiny, and then it has a lot of sensors. Okay, so that's the one that I'm using. It's kind of very interesting because it's pretty. As microcontrollers go, it has one of the higher end microcontrollers with good amount of sensing, and yet it is kind of tiny. So sweet spot in terms of what it is able to do. Part of its power comes from this block which exists on the right hand side out here, which is from this company called uBlocks. It's a module which has a processor in it and integrated antenna. So this NRF 52840, this is from a company called Nordic, and 52840 is one of the chips which has ARM's Cortex M3 or M4, I forgot. Those should be here somewhere. Yeah, Cortex M4. So ARM Cortex M is the embedded series. M7
Recording in progress.
The highest end version. M4 is sort of pretty decent. Usually they go up to maybe a few hundred megahertz. That's the top thing. More typically like tens of megahertz to, let's say, low 100 megahertz. So this device that you are seeing, the processor part, the microcontroller part, is really that tiny little thing from a different company, and it has integrated antennas and all. And rest of the stuff is really power and USB and sensing support and all. It's a very common way of doing things. It's unfortunately it doesn't have Wi-Fi, so I think one of its sister boards is something called Nano IoT, and that one, the module they use has Wi-Fi in it. Okay, so whenever you're working with these kind of hardware, it becomes super important to exploit them, to read the manual. Okay, there's way too many details, and without understanding what your peripheral does and all, it's very hard to exploit things, right? This is not something we face so much in our normal programming because you don't tend to optimize for power and performance to the same extent, but B, companies like Microsoft and Apple and all, kind of they deal with a few options and they try to hide things away. Here, there is just way too much fragmentation. So, I mean, this Nano 33 BLE is one of probably a few hundred boards that Arduino supports and such operating system supports. It's very hard to design operating systems which maximally exploit the capability. So sort of diving deep and understanding these platforms pays off a lot. And unfortunately, it requires understanding many different levels things, right? I mean, at first level, you have to understand this board. Next level, you have to understand this uBlocks thing. Then you have to understand the processor. So it's not like one level. It's like this is chain, and you have to kind of really, to be able to program it. The processor part is this NRF 52840, which is what one has to sort of understand. And likewise for the different sensors. So one consideration, at least for this type of MCU platform, is really things having to do with energy and power. Okay, so I'm going to spend some time on what are the issues there. I used to teach a course which was entirely devoted to low power computing and all, but I haven't taught it in a few years now. But of course, there is tremendous interest on the power side of things. Okay, so at least for embedded devices, there are two reasons we worry about power, energy, such things, right? One is battery life, and that's a complicated thing, right? I mean, batteries are rechargeable, so you could also you can think in terms of like how much time before we recharge, right? And the other one is thermal issues, which is things getting too hot. As you probably noticed, some of our tinier devices get too hot to even like just be against your skin, for example, right? And in some applications, the heat part does matter, right? I mean, if there is an implantable, that heat not going anywhere can have damage the tissue, for example. In other cases, yeah, actually, what else can thermal failure do? Like things heat up.
The device itself.
Device itself, yeah, it can be destroyed. Or more commonly, its longevity can be affected. So electronics are also physical devices, and heating can cause total failure like burnout to where this age goes down. Right? I mean, how long it will last. Electronic devices, as they operate, age, their performance degrades, and when you, like if you buy a server processor, then they quote your data for a longer period of time because servers are deployed for longer duration. On the other hand, let's say you're buying a smartphone, it's a shorter time horizon. So aging is taken into account when manufacturers make guarantees about the performance, but it is always under some band of temperature and all. And so if thermal stuff happens, that's an issue. Modern devices, processors have thermal throttling capabilities built in. So if it heats up, then they will react to it. Any thoughts on what would you do to react to thermal event?
Decrease clock speed.
Decrease clock speed. What else? Down. Decrease voltage. Right. I mean, these are some of the things that you would do to kind of lower the stress. In fact, I mean, thing I have encountered on my iPhone, these kind of events, particularly if you leave it in sun running something, then kind of puts it. So thermal throttling is a valid thing, and battery life and also battery age. If you don't use the thing properly, then battery may die sooner, as in not like exhaust, but like its capacity to hold charge degrades. Okay, so there are lots of like effects like these which kick in. So in computing systems in general, but so these power and thermal issues are not just in embedded systems anymore. I mean, obviously laptops, servers, for different reasons, right? For big computers, you worry about sustainability, right? I mean, if the data centers now consume roughly 5 to 6% of industrial energy consumption. So even big computing has lots of power and energy related consequences, but they really have more to do with running cost and carbon footprint and those kind of issues. Whereas for embedded devices, it tends to be more like battery life, thermal events, so different reasons, but they're present. So, so in computer systems, usually it's very common now to have reduced functionality modes. So reduced functionality modes may exist for all parts of the system, for your hard drive, for your memory, for CPU, for sensors, all sorts of things. And they may range from idling the system to stopping the clock to powering off all the way, and so on and so forth. And some entity, some runtime monitor, either the application or the operating system or some piece of hardware logic, has to decide how to transition between these states, right? So it kind of monitors what the overall context is, and based upon that, puts things into the right mode. If there's a thermal event happening or something like that, or for example, just trivially speaking, maybe I'll run my system in the low power mode all the time, and then when I detect that the user is going to do something, then I kind of ramp it up, right? So some entity has to do it. Like I said, application can do it, OS can do it, hardware can do it, and some combination thereof. There are trade-offs. For example, if the application were to do this stuff, then it can just do it for itself. And oftentimes, coordinating with other applications matters. So a single application cannot do it effectively. So then OS has to somehow appear in that. The problem with OS is sometimes if things go awry, it may not react properly, and other issues can kick in, which is that it doesn't have low-level hardware knowledge. So then say, okay, maybe the hardware should do it. Hardware can react very rapidly, that's the good part, but then hardware lacks application level knowledge. Like for example, maybe right now I'm doing my keynote presentation, don't put the string to sleep, right? I mean, hardware would have a pretty hard time knowing that kind of contextual information. So power management across these states really requires a coordination between all these layers, and people have been working on it since the 90s. Continues to be kind of a challenging issue because it's very hard to get it right, and there are lots of bugs and all come into play. Just to give you an example, a very common form of bug in Android used to be something called a power lock bug. So the idea was the following: there are some applications which they know they don't want the system to be put to sleep because they are doing something important. Like, for example, again, my keynote example, I don't want the screen to go to sleep, right? So the way the OS in that case provided a mechanism was that the operating system can take a power lock. Lock comes, those of you who have done an OS course, this abstraction comes from software. I lock a resource, right? So in Android, it was like I tell the OS, don't shut this thing down. The problem is, so if I power lock I take a power lock, and then I die, or I hang, right? My code hangs. So then the system just burns power and all, right? Needlessly. So power lock bugs were a problem. Attacks happen this way, right? I mean, a malware can seek to run out the battery in your system. So proper management of power or lack of proper management of power is also a security risk of forms, right? Then another thing which happens is the following: if you let an application monitor power consumption of the platform or some other entity, then they can learn about what other parties are doing. So a very pernicious form of attack on embedded systems has been what is called as power analysis attacks. And kind of the idea is that what if I can see how much power consumption the platform is having. I can do it many ways. These platforms are deployed outside, maybe I can tap into the battery wire. Maybe I can look at the RF emissions, which tell me something about the power consumption. Maybe I have some malware running on that platform which is able to examine the power sensor. Okay. The idea being that if I have a running trace of power consumption, and then some other, I can learn a lot of information, right? I can learn the behavior of the application. I can even detect what data they are working with. There have been attacks which have extracted cryptographic keys using it. So power is a vector of attack also. So for the past sort of 20 years or so, starting with just optimization of power to now worrying about security and these kind of things, power has been a lot of important and actually a good area for exploring some projects. So basic strategy tends to be save power by changing power state. Philosophically, if you think about it, it's good for a system to adapt its mode so that it only uses the power that it needs and does nothing else, right? So if I'm not doing anything, I would like to put the system to some low power mode. If I'm very active, I want to kind of go into a high power mode. Now this is where, by the way, the security threat comes in, right? Because I manage the power state based upon my needs, so therefore someone who can look at the power mode knows what my needs were and therefore can speculate about what I'm doing, right? I mean, it can begin to know something about my state. So that's where the deeper connection is. Back out here, so I need to change the modes, and this problem is called as dynamic power management. Essentially, at runtime, I have to manage power. Okay, so that's what it is referred to. So one version of it, what he said some time ago, change the frequency. Okay, frequency scaling. So essentially, you get a processor, you change the clock frequency. Now, if you think about the way these systems are designed, there is a clock source, which is usually what? Where does the clock come from?
PLL.
Huh?
PLL.
No. PLL.
Crystal oscillator.
Crystal oscillator. Yeah, that's the most common. Yeah. So crystal oscillator is a source. PLL amplifies, multiplies, or divides the frequency, and then you distribute thing. And if you look inside, like that NRF processor, you'll see there are many different clocks in there. one going to the core, some other going to the USB, radio, different peripherals, and so on and so forth. So here we are talking about scaling the frequency, which is going to the processor core. And essentially, loosely speaking, power is proportional to frequency, right? I mean, you can think of it, my clock decides when I'm doing the work. So if the clock is faster, I'm doing work more often, right? Let's say every clock tick we do an instruction, right? So it's affecting that. So and that each unit of work takes some amount of energy, right? Charging, discharging some transistors and the capacitors. So power is proportional to frequency to the first order. Dynamic frequency scaling refers to scaling that frequency so that I can change the performance of the system. So for example, if at some time low latency is needed, I will boost the clock frequency. At other times, if I can be more leisurely, I'll lower the frequency. It's kind of obvious. Getting it right is not necessarily that easy because now I have to change all that frequency, right? Manage that, I have to decide when to change it. If I am too slow in reacting, I may miss deadlines, or the user may get annoyed, right? I mean, all those kind of issues come into play. So that's the idea behind frequency scaling, and in particular, dynamic frequency scaling. The problem with frequency scaling alone is that what's happening, right? If you think about it, I am doing things slowly. So instead of a, let's say, a 1 megahertz clock, I have a half a megahertz clock. So I stretched things out, but I'm still I'm still doing same units of work, right? Same number of instructions. And if each instruction needed certain amount of energy, right? Some charge to be moved or not moved, it's going to take the same amount of energy, it's just over a longer period of time. So it's going to lower the power, right? Energy divided by time, but it's not going to affect the energy. But since I slowed down the clock, I actually have more time, right? So maybe I can operate the circuit in a more efficient mode. And that's the idea behind dynamic voltage frequency scaling. So if you go back to your digital circuits, digital logic, the speed of a circuit, digital circuit, is decided by the critical path, right? Input to output, you do the longest path, whatever is that delay, that decides the clock. But that is decided by the speed of the gates. The speed of the gates depends on the voltage, right? If I give a higher voltage, the gate is faster. So if I have lowered the frequency at which I'm operating, I can afford to operate my gates at a lower speed. And therefore I can operate them at a lower voltage. And then I can reduce the energy taken for each one of those units of work. So I'm spreading, not only am I spreading out, like let's say I have n instructions, not only I'm doing now that those n instructions over twice the time, but the energy for each one of those instructions is also being lowered, okay? Because frequency scaling alone lowers the power because I have more time, I'm spreading the energy over longer time, but it's not helping in terms of my battery life, not the first order. Whereas this strategy lowers the energy taken also. So this is called as DVFS, or dynamic voltage frequency scaling. So this came first. If you kind of go back, probably dynamic frequency scaling systems emerged in early 90s, and dynamic voltage frequency scaling systems emerged in late 90s, like a 10 years.
Can you tell this realistically, like how it works in practice? I know that, like, especially in embedded systems where, you know, things are already pushed down to a very low voltage because trying to operate like sub-threshold. How often is this? I know that, like, also in systems like leakage power is a very large.
Okay, so you obviously know a lot more, but let me attempt to explain, and for benefit of everyone, I'm going to explain a little bit more slowly. Okay, so one issue is, yes, this is very challenging to do. Now, part of the challenge out here is the following. For any given voltage, my system can operate at some max frequency and no higher, right? Because for any given voltage, the gates, the logic gates are going to have some speed, and therefore my critical path is going to have some delay, and I can't operate faster than that. So if I'm doing this dynamic voltage frequency scaling, I have to scale the voltage and frequency in coordination, right? I have to set the voltage so that it can sustain the chosen frequency. Let's say frequency is my primary norm. I'm going to use the frequency as the accelerator, and I want to jack it up, bring it down. I have to set the voltage accordingly, right? If I'm jacking the frequency up, then I have to jack the voltage up, but not excessively excessively, because then I'll waste power. So I want to make the voltage just high enough to meet the new frequency. It sounds easy, but it's super hard. The reason is this mapping between frequency and voltage depends upon temperature, depends upon the specific chip, right? I mean, I take 10 copies of the same processor, you're going to see differences. So there are special circuits that people put to figure this mapping out for that particular piece of hardware. So that's one complexity. Second complexity which comes, which is a more nuanced point that he's making, is the following. And actually I'll talk about it a little bit later. Power of a system is not simply strictly proportional to frequency. It also has a constant term, right? Even think about it, right? Even if I stop the clock to my my processor, it still consumes power, right? And that is a static floor which exists in any system, right? It's kind of like this the penalty for being on, think of it like that. So this is this constant background power. The many sources of it. You mentioned something called leakage power. So the gates, transistors are made of diodes, and diodes, even when they're off, have some tiny amount of current which flows in the reverse direction. Okay, so there's always some current which is going. At a higher macro level, there are other examples of it. How many of you have heard the term vampire currents? Heard of it ever? No? Okay. Vampire currents refer to the fact that all these power adapters that we have in our society, when they are plugged in onto the wall, but no device is plugged into them, they still consume some power. And accumulated over lots, like literally billions of such devices, it adds up. So in recent years in EU and places, they have begun to clamp down on it. Okay, so they want power adapters to shut down when they are simply idling. Okay, so these are all examples of background power consumption which eats away into things, and same thing occurs in electronic devices. There's a background floor and which limits things, right? So if I take frequency scaling or voltage frequency scaling to the extreme, let's say I spread it out a lot in time, at some point the limit is not this power, it is that background power. So you should take this thing to the extreme. Hopefully talk about it later on, but there are a lot of nuances under the hood. So all of this leaves you with three strategies now. Scale frequency, right, which we could do by playing with PLL or playing with the crystal oscillator or some other such thing. Do a coordinated scaling of voltage and frequency. And the third one is shut the system down, shut off the power supply, right? I mean, or so stopping the system, right, or stopping the clock would be another strategy, right? And these are kind of three tools at your arsenal. It's equivalent to walking slowly with more efficiently, I guess, and then kind of not walking at all. So, so those are kind of the basic strategy, and every particularly in the microcontroller world, you will find that there's a very important part of the data sheet which just goes with these power management. It will describe what kind of features. Some of these processors have on, so firstly, shutting the processor down, very common. There are many modes of shutdown. So one thing that they do is everything fully on versus peripherals shut down, everything else fully on, versus maybe memory is also brought down, right? I mean, so there's different degrees of shutdown. That's one part. Then changing the frequency, that's easily done. They support that. Changing voltage and frequency is trickier because the voltage has to be changed. Where does the voltage come from? What supplies voltage to the electronics? Regulators, right? Regulators are circuits which take poor quality voltage from battery or whatnot and convert it into a stable, good quality voltage. So usually you will need to have a regulator which is software controllable, which can change the voltage. That means, now usually regulators are put on the boards, which means that the board has to support it. But there are processors where regulators are on chip. So depends on what you're doing. Some processors have native support for DBFS. Other processors rely on the board providing adaptive power supply, right? In order to be able to do it. So here you would see that NRF gives a whole bunch of power management features, range of power voltage. I'm kind of just reading on-chip regulator, so it has on-chip capability for voltage regulators, which it can mess with. Automated peripheral power management. Usually in these systems, the processor core is just a small part of the overall system. So power management is not simply an issue for the processor, but there are counterparts to other things. Also, let's say you have camera. You can change the frame rate of the camera, you can change resolution of the camera, you can change black and white versus color, right? I mean, all these kind of things. If I have some other sensor, maybe I can change the sampling rate, right? So there are analogous stuff for everything. One challenge which, let's see, couple of things that a lot of attention is paid is when you change things or put the system to sleep, how much time it takes, right? So there is a term called duty cycling, which refers to that I put the system into an off state, on state. Sounds great, but if it takes a long time to switch between the two, then a lot of benefits are negated, right? So I need to be able to very rapidly put the system to sleep and wake it up, okay? So startup time matters, and startup time can be bad because of circuit reasons and because of software reasons. So let me talk a little bit about both of them. Actually, if we're at the halfway point, you guys want to take a break? No one cares, or you do? Yeah, let's do 5-minute break.
It's nice seeing all of the features that are considered for devices like this, right down to power consumption. Especially considering as we increasingly take into account like environmental considerations. If we can make the machines perform just as well, if not better, while also improving their efficiency, that will.
Yeah, I mean, by the way, I mean, these are things that computer system architects totally worry about. These are seriously worry about.
100%.
Yeah, I mean, and not just an embedded device, like you said, I mean, data center people worry about.
Yeah, all different kinds of devices.
Standards that like LVO will have all sorts of
I think part of it is that it has to work so that it synthesizes on a specific part of the. Yeah. I think there's like
which hardware you're using to, like when it actually synthesizes our scale, right?
Okay.
Oh, your RC constant. Yeah, your R. Yeah. What's the reason high wave? High wave. That's linear to voltage. Right? Well, in most like loss
Yeah, for that. Try to eat a light lunch myself. I reckon I'll eat a global before yeah, Tuesdays and Thursdays from 9 p.m. to 11 p.m.
Oh wow.
Yep.
Like this is a time conversation. It's a this is ours. I know this is not technically accurate, but
Probably my statement club is East Bushwood Drive. I manage the one on the yeah. Yes.
Oh no.
Actually, had a good amount of success too.
Oh, I guess that's really good.
Yeah, well.
Yeah. The important thing is you have fun.
Okay, let's restart. So there was a question about why is wake up time important. So the issue is the following, right? I mean, think about a very simplistic strategy. I'm going to put the system down to sleep. And now the question is, when should it wake up? Now, a very common well, firstly, in general, I don't know where it needs to wake up, right? I mean, unless the system is insanely predictable, more typical would be some event happens and then I react to it by waking up rapidly to it, right? I mean, some sensor event comes in, for example, or a packet comes in over the radio or something, then I want to wake everything up. So if I'm very slow in that wake up process, then during that wake up time, I'm burning power needlessly, right? And I'll come into it why that might happen. And the second thing is I may miss deadlines, right? I mean, so we need to do that. Now, why does the wake up time come into play? So I alluded to there could be circuit reasons and there could be software reasons. Circuit reason simply is that some of the circuits have capacitors, or they may be kind of like mechanical devices, like you had mentioned crystal oscillators. Crystal oscillators is piezoelectric crystal which vibrates. For it to vibrate onto a stable frequency, it takes some time. So if you even if you design the circuit properly, it will take potentially milliseconds. And if you don't design it properly, it can take longer to come to a stable frequency. So if you look at the frequency output of the crystal oscillator, it's kind of gibberish and then stabilizes. Voltage, same thing, voltage regulator, right? There are capacitors in there and all need to charge up. So if you look at the voltage, it takes time to stabilize. So circuits have some time it takes, let's say order of milliseconds. Then there are other parts of your system, like let's say radio. If you put it to sleep, when you wake it up, it needs to resync with the rest of the system, like let's say to a base station and all. That can take time. These are sometimes just protocol related things. And finally, software. If your system boots up, then boot up it has to take time. And in fact, it's kind of a non-issue nowadays with like our phones and all. I think the smartphone really did a great job that you press a button and it's instantly on. You guys are too young, but if you just roll back 10 years, really, it wasn't like that. I mean, and even now, if you boot Linux and Windows, it takes a distinct amount of time, right? So this notion that I can shut the screen of my laptop and bring it up and it's instantly on is relatively recent, okay? And a lot of optimization at the OS level had to go to make that happen, okay? Very rapid saving of state and then restoring the state, techniques to hide latency so that even like getting the more important things first in front of the user and while the rest of the system recovers. A lot of optimizations happen, a lot of rethinking of things. Like for example, one source of latency used to be that when the system shuts down and you wake it up, then the IO devices need to have to be reintegrated into the system, particularly like USB devices and all. So they did a lot of optimizations and all, and smartphone was a big driver for it. Like, I mean, we wouldn't want to power it off, like, right, and then press a button and wait for seconds. I mean, it would be just awful user experience. So it used to be that even a hot reboot, like shut down and wake, soft shut down and wake up, used to be tens of seconds. Now, at least that kind of stuff is instantaneous, right? Hard reboot is still expensive to do, but kind of saving the state and one big role was played by memories. Memories that you can put into a low power mode, and then they can last for a long time. And then when you start, you increase the voltage, and they can immediately kind of come up with it. So the memories in your system have these low power modes, and also a combination went into optimizing this startup power so that you can make shutting down efficient. Likewise, changing clock frequency and changing voltage suffered from the same issues. I recall, I mean, my group worked quite a bit in low power systems. So very early on, actually, dynamic power management was one of the very first people to work in it. The delays used to be tens of milliseconds. Okay, I mean, in those early systems, due to the combination of all these factors and all. So if you change voltage during that time, there was a distinct time of like many milliseconds where we couldn't do anything. We just had to wait for the voltage to change. Okay, so all those things have disappeared now, right? I mean, because power became such a dominant concern that all across the hardware software stack ended up getting optimized. So that's why kind of at the startup, if startup time, if whatever time to put it to sleep and wake up is too long, then a lot of these other or time to change voltage or frequency settings is too long, then a lot of these benefits get totally negated. Okay, so that's the underlying story. Examining what modes are available and all is pretty important. And also the other thing is, any given OS is like if you think of like, let's say Arduino, okay, it's not a baby OS, but I'll use that as an example, is designed to run on many different processors and all. So it picks a sort of a common denominator which it can support. But any given processor would have a lot more modes and all. And so seeing how they are being exposed, can you make use of it and all, pays off dividends, particularly if you're designing a system for more extreme requirements. Okay, so hopefully that answers the question. So within NRF, usually these processors have some sort of a power management unit at the hardware level. So there's some stuff happening there. In sometimes there's a system level. In Apple computers, for a long while they used to have a chip called power management. If you have a Mac, you know, like they have this thing called PMIC reset. There are like these modes where the power management hardware goes berserk, and you have to kind of give it a kick So to say nowadays it's just part of the regular chip. So there's special hardware support there. Some of these things just have to be in hardware because if software hangs, then the whole system can go can misbehave. So on NRF, in the processor itself, there is this PMU which kind of interacts with everything else. There is a pretty elaborate structure of sleep. So like we think of like, oh, I put the processor to sleep, but there are many different modes or different implications. When you come out of sleep, what was remembered and what was lost, right? I mean, if I'm willing to think of it like before I go to sleep, I have some state, right? Some settings, right? Some data. If I'm willing to forget all of it, then the task of going to sleep and waking back up again is easy. If on the other hand I have to preserve it, that's where the hard thing sort of comes in. So a lot of these things kind of revolve around what is it that I'm putting to sleep and what is it that I'm willing to forget there. So you see all these modes and the corresponding current requirements. Loosely speaking, the deeper in sleep you go, the harder it is to come out of it, the more you will save while you are in that mode, and quite possibly you will forget more. Okay, so these are kind of the three very loose trade-offs. Now think about the following. Let's say I gave you a choice of two sleep modes. One which says, so let's say a normal power consumption is 1 amp. I say, okay, you have one option of going to sleep. It will cost you, when you are in that mode, it's 0.1 amp and it will take you 1 microsecond to get to it. There is another mode which it will take you 10 microseconds to get to, but you would be 0.01 microamp. Now think about, you have a decision making thing to do, right? Should I go to the deeper sleep mode with lower power consumption but a higher cost of coming out of it? Or should I go to a shallower mode? So what do you think? How would you decide that? This is what would be called as a sequential decision making problem, right? I mean, you are given your current state, you have to kind of decide, given these choices, what do I do? And usually choices are a lot more elaborate, right? I mean, I'm giving you a very simplistic example. So intuitively, what do you think should the OS or the system consider?
Yes, it might depend on how often real-time critical tasks I need to be performed. Like if there's something that happens pretty often, I want my time to wake up to be small.
Yeah, so it's a more nuanced answer, but you're in the right direction. So if the next event when I have to wake up is going to come too soon, then there's no point in going into a deeper mode because it takes a lot of time to come out of it, right? So that's one aspect of it. Another aspect of it is when the next event will come is very predictable, right? If I knew precisely that the next event will come at 4 p.m. and I know my wake up time is 1 minute, I'll just wake up 1 minute before 4 p.m. and be ready for that, right? So predictability is an issue. How far in the future is it? Is an issue. There are a bunch of these considerations that you have to take into account. Early systems, like I did some work in this space in like very, very early days of this field, right? Late 90s. When we were using some stupid simple systems, thresholds and all. If you look at what happens now, companies like Qualcomm have neural networks trying to figure out the user behavior when the user will next apply reinforcement learning and all these fancy methods. So I mean, there is just so much at stake that there are more and more advanced methods being used to do this decision making. Okay, and of course the systems are a lot more complex, right? I mean, there are lots of moving parts, and they depend on sensory input, and network input, and user input. So the decision making is just complicated. So that's one factor. When will the next event come? What else? Platform characteristics, right? I mean, all this data, right? I mean, what are the precise current numbers and the on-off times and stuff like that? Those are going to matter too. Same, it's not just for processors, it's also for things like, let's say, a hard drive. Should the system put the hard drive to sleep or not? Right? I mean, if I spin down the hard drive, then when the request to read or write a byte comes, that disk needs to be spun off. Okay, during the time the disk is spinning up, it takes a higher current because it's working against friction. So many systems have the characteristic that during the wake up time, they may actually have a surge of current. Okay, actually processors do too. If you look at a processor, put it to sleep, wake it up, for a short time it's going to have a peak in the current. Okay, and that's the onrush that is happening. So very complicated. Then there are implications on batteries. If you draw current smoothly from a battery versus in a burst, batteries are electrochemical systems. They have ions moving around and all, right? There are ramifications there also on the health of the battery, or the energy you get out of the battery. So the real optimization problem under the hood is not even just the processor and the memory and the sensors, but also the battery. So all of those things go there. So I guess all I can say is it's a darn complicated problem, and I can just give you kind of a high-level glimpse. And the hardware, the OS, and application, they all work in concert to sort of make this happen. Let's see. Yeah, these are just some plots of showing the different current consumption. So don't really matter. It's good to know roughly for the processor you are working with what these data points are, what the sleep mode is, what are the relative power consumptions, how much time it takes for you to go back and forth, so that you can do something intelligent. Right? Now, one thing I wanted to highlight is that there are two separate sets of issues, and one has to be very careful about them. One is the issue of energy, and the other is the issue of power. I talked about it a little bit earlier, right? I mean, I can have low power, but energy remains the same, right? In some cases, energy matters because that affects how much work I can do for the same battery. In other cases, power matters because it affects the thermal dissipation and stuff like that, among other things. So I want to touch upon that a little bit. Let's say I give you two processors. This is an old processor from Intel when Intel used to make ARM processors. Okay, so this one, 1 watt, 1 gigahertz, 32 bit. Okay, you can take like a modern instance of it. I just don't have the data. Here is a tiny microcontroller. It's a processor for 80 mega, which I think Arduino's, the original Arduino's use. 50 milliwatt, 8-bit, 10 megahertz. Right? So looking at this, which one would you pick? Now, this is lower power, 50 milliwatt, right? Versus 1 watt. This is lower power, but that's not kind of the whole story of it, right? I mean, if I stare at it, it's a much slower processor, and it has fewer bits, right? So it does 8-bit operations, and that one does 32-bit operations. So now, really, what matters is what am I doing with it, right? So now I have 3 examples out here. There is a FFT, there is a CRC, and there is an FIR filter. If you don't know what they mean, doesn't matter. Think of them as some reasonably complicated features of computation. Okay, and here, and you have on a log plot on the y-axis energy, right? Execution energy, right? So what you see in this case is that 80 mega takes orders of magnitude, a couple of orders of magnitude more energy consumption, right? So if I were to think in terms of energy per unit work, it's insanely inefficient. And my 32-bit stuff is pretty good. And the reason is it's doing sort of more powerful operations, and it has presumably more architectural features to gain performance, right? I mean, so all of those things sort of kick into play. So now I would say, okay, so which one should I pick? Okay, so if my system was designed for just keeping an eye on the world and doing something simple, clearly I'll pick the microcontroller. If on the other hand it's designed to do some hefty computation, clearly the bigger processor benefits. And you would generally see the story play out again and again, right? If I have to send a bulk file, Bluetooth low energy is awful. I'll pick Wi-Fi. If on the other hand, I have to just keep an eye on a sensor and occasionally exchange a bit, then BLE excels, right? I mean, so systems inherently tend to be optimized for some operation point, right? Some are optimized for high performance, say Porsche, versus some are optimized for efficiency, sustained, like let's say a solar car, right? So same story plays out here. It's something natural about the system that they are kind of optimized for some operating point. There is of course more to the story out here. The microcontroller, its sleep power is very low and it can go into sleep very rapidly. Bigger processors have more states, they have more registers, and also they take, so firstly, even when you put them to sleep, they still have that background power consumption, so they take more power, and also they take more time to transition in these things. So generally speaking, a system optimized for higher performance would also have a higher baseline power when put into some sort of an idle mode, and is going to be costlier for it to move in and out of that state. Whereas simpler systems are more agile in that regard. Low-end microcontrollers, nowadays you can get microcontrollers whose sleep mode power is in picoamps or a fraction of an nanoamp, right? And they can get in and out very, very quickly. So now the whole story becomes even more complicated. If you're designing a system, what should you do? Which one should I pick, right? Should I pick this bulk efficient but bad in sleep mode thing, versus should I pick something which is like great at tiny computation, great at sleep mode, but awful at bulk computation? Now this is a dilemma that we face again and again in systems. One place where we face it is in memory, right? We have SRAMs which are fast, we have DRAMs which are great at bulk data storage but are slow. What do we do? We use both. We put them into a hierarchy, right? We create a cache hierarchy. Same thing with these, right? I mean, I can combine them, right? I can use both and be intelligent about switching between them, right? The always vigilant tiny processor, and then when the bulk event happens, so that you can think of it like maybe I'm monitoring some sensor data coming in. Most of the time it's uninteresting. I collect it, take a quick look, move on. Microcontroller can do it great. Once in a while there's something interesting in it. Then I wake up the big guy, okay? And you can imagine various splits of it. Maybe my tiny guy can even do a tiny ML model and do some simple thing, so some simple object recognition, and only if with reasonable probability I think it is whatever an enemy tank do I wake up the big guy for a more accurate assessment of the scene, right? I mean, so I can organize things like this kind of hierarchy where we wake up the more powerful entity as and when needed, and of course arrange for the necessary intelligence to make it happen. So all of this goes in. So what that leads to is something that researchers from Google some 15 years ago saw labeled it as energy proportionality. Kind of the idea is that I want my system to be energy proportional. It should use energy proportional to the work it is doing, and if the work varies with time, and if the system is energy proportional, then it would adjust itself, right? I mean, that's kind of like a ideal goal that you would want. Hard to achieve it because of reasons that we discussed earlier in the class, which is there is this baseline power, right? So if I have a Mustang or a Porsche, just to keep its engine on so that it can take off quickly, there's a baseline power which is much higher, versus if I have a more fuel efficient Accord or something, then its baseline power will be lower, but then its peak performance will also be lower, right? So ideally I would like to be able to switch between them. So same thing out there. So looking at a phone, if you look at the workload, it's non-uniform, right? And what's happening out here is, as the user is interacting, there are times at which there's a burst of activity, maybe there's some animation happening on the screen, clock animation, all of that is happening, and then most of the time system is doing nothing. So most of the time I can operate with low performance, and then occasionally I have to operate with high performance and then rapidly go down. I'm showing it with smartphones, but you can kind of think of it in context of any other embedded system. Also, sensor data comes in, there's a burst of activity, like go into a quiescent mode, not quite happening. So, and if you look at like one of the new things on the smartphones the past 2-3 years has been this adaptive refresh rates. So actually that's a cool project direction to also think about. So phones, the screens, the displays, right, the OLED or LCD displays, they have a refresh rate, and traditionally they were just a fixed refresh rate. But the display power depends upon the refresh rate. So one of the things that happened, I think starting 2-3 years ago, is that the refresh rate became adaptive. The latest iPhone 14, I have that, its lowest refresh rate is 1 Hz. Okay, you can just truly drive it down, because if the screen is just static, not doing anything, then it doesn't have to be big fast. On the other hand, if you're playing a game, it needs to jack up. So nowadays, even screen, they do similar kind of smartness. Depending on the content on the screen and the application being done, you're kind of jacking up the refresh rate and bringing it down. But sort of originally, kind of stuff was driven by what's happening at the processor level. I can clearly afford to make the processor operate at a lower frequency or at a lower performance level when not much is happening, and move up to a high thing when there is activity.
Okay, good. So I was wondering, like, what level is something happens on? Like, do applications normally have control over something like this?
Do applications work?
Have control over something like this, or is it normally, because it sounds like it has to be.
Depends on the system, okay, and depends on the OS designer's philosophy. Apple's philosophy, if I were to summarize it, don't burden the application. Okay, so the power management cleverness has been in the past. Android had been more on the other side, gave more control to the application with associated notifications. So there's no one answer to it, and you can make a case either way. That application has information which can better do it, and the other one is that, you know, OS has better global information, and therefore OS is the right place. There are papers just talking about philosophically at some level what's the right place to do it. So there's no one right answer. And you could also argue that applications often know about the data and when it will arrive next, so it has additional information. Maybe application can inform the processor, inform the operating system. So yeah, good question. I don't have a clean answer to it. I think right now, a hybrid. I think much of it happens at the OS level, but applications certainly play a role. At least, at the very least, by giving a hint. But in Linux and all, the OS does allow applications to control these things. To give you an example, okay. So I talked about the screen refresh rate. My student is working on it for some work. And my understanding is, on iOS, application can tell the OS, and I think Android is similar, can tell the OS roughly what we want, high refresh rate, medium refresh rate, low refresh rate, but the precise setting is taken care of by the operating system because it is done at a slower time scale. So, in Android, the situation is a little bit more complicated, it seems like. There are things you can do from the world of Android, as in the Java side of things, but then there are more things you can do if you're willing to write the so-called native code, the NDK, and then you can write deeper. So those differences too. So, yeah. So anyway, I think that examining what kind of scaling opportunities are available in all these platforms, either on a smartphone or even one of these embedded platforms would be cool. I think the refresh rate, if you have a recent Android or like you're saying last 2 years, this year or last year, Samsung or iPhone, then this you have adaptive refresh rate, for example. Okay, so energy proportionality, the challenge that we face, and again at a philosophical level, like I said, the term came from Google from a data center perspective, but kind of the idea is that any given system, right, processor, server, whatever, right, is designed for some operating point, right? So in this case, I have like a big thing, and it's with dynamic voltage frequency scaling, let's say performance power curve looks like this. It's a big guy, so it has a higher baseline power consumption. So you see the curve is very high, right? I mean, there's a base. It's just a schematic way of saying, but what I'm trying to say is there's a high baseline power, and then it's giving me a power performance, right? But maybe I also have a simpler processor, which is more efficient, so it's overall lower, and it lets you span the space at a lower performance. So I have now 2 cores. One is a big core, maybe deeply pipeline, superscalar, whatnot. A simpler core, maybe it's non-pipeline, single issue, whatnot, and they just might look something like this. They have just different operating points. And then, moreover, you can imagine that the 2 cores may have the same instruction set architecture, so that my same software can run subject to memory limits and all, or they may have different operating system, different instruction set architecture. So, all of these things kind of currently exist. So, you will find sort of generically that some of these chips have, let's say they may have an ARM core or multiple ARM cores, but some of them may be big, some of them may be tiny. They can run the same code, but just with different performance. Apple's M series stuff, for example, has big core, small core. Snapdragon from Qualcomm, similar story. Okay, so they have big core, small core. The ARM's official term for it is called big dot little. Okay, so big guy, little guy. And then platforms often have this heterogeneous code, which may have a different ISA, and it's really optimized for something else. A great example here would be on iPhones, they have the so-called motion processor, which is the one which handles the data coming from some of the sensors, the inertial sensors in particular, and this is where they run some models to extract like your activity state, like that. Okay, so now our typical system then has some heterogeneous cores and some main application cores which may come in different sizes, heterogeneous. I picked the Apple example. The same thing is true with Samsung, Qualcomm. In Qualcomm Snapdragon, they have big, little, and then they also have these what we call as hexagon DSPs. Okay, these are probably a typical Snapdragon chip may have half a dozen, if not more, of those hexagon DSPs. Most of them you don't even get to program because they're only accessible to Qualcomm or some close partner. But some of them, so typically they handle like microphone workload or sensor workload. So you have this structure now where big core, little core, and then heterogeneous cores. Okay. Yeah. Sometimes these heterogeneous stuff may not even be programmable processor. They could be more like neural accelerators and all. They are programmable not in terms of like writing a standard program, but like configurable with, let's say, weights of a neural network. So that's this particular, like I gave an example of TI OMAP, which I think is already example of it. I think some of the Amazon products use it, if I'm not wrong. But in any case, there are plenty of examples of these chips. So the idea behind then energy proportionality then becomes is that given these resources, potentially heterogeneous, as in different different ISA even, I will bring the right resource at the right time, depending upon the workload. And of course, you can imagine, again, a smart strategy would perhaps will not just be reactive, but it will anticipate, right? I mean, so for example, if I think someone had made the point that maybe I know when things are happening in the future, so I can kind of begin to make some predictive strategies out here. Other smart stuff like, as the user is bringing the finger closer, right? I mean, these are capacitive screens. Maybe I can detect that the finger is coming closer and then switch the processor to a hostile mode up ready before the finger touches the screen. So there are all sort of clever stuff you can imagine doing, but the basic idea is that now I dial down the resources according to the activity that is happening and try to hide the effect of latency. Okay? So that's the idea. Now I'm showing all these examples in context of a smartphone and all, or talking about a embedded system. A lot of these ideas are equally applicable to, let's say, a data center. I'm a Google-sized company operating a big data center. I have thousands of servers. I'm not going to keep all of them up running simultaneously. I'm going to use them as resources and bring them up and down. If suddenly there is a spike because it's a Super Bowl halftime, then a different reaction happens, right? I mean, suddenly some event happened, there is news blaring all over, I activate things, right? So individual servers are pretty inefficient. So if I just were to keep all of them up and idle, I'll be burning a lot of baseline power. The idea is I'm going to shut things down, put them into really deep mode and keep a subset up, but then manage which one to activate and then to activate. So actually energy proportionality, as I mentioned earlier, was a term that people from Google sort of introduced. So big dot little is what the architectural concept got to be known in terms of processors where cores of two sizes, a big and a little, with the same instruction set architecture, were married together. I think it's probably a trademark from Amazon, sorry, from ARM, but you will find instantiations of it. So Samsung Exynos chips, Qualcomm chips, they all kind of have versions of it. Details don't matter, and this particular chip is several years old, but in this particular case, they are using A7 and A15 cores. So ARM's A series cores are what are called as application cores, whereas the M series cores are for embedded users. So A series cores have all the features you expect from a more general purpose processor, okay? And A7 and A15, loosely speaking, A7 is simpler and A15 is bigger in a variety of ways. Same instruction set, but different microarchitectures. A7 is in order 8 to 10 stage pipelines. Does anyone know what in order for processors mean?
One instruction can only occur after the next instruction.
Correct. The instructions are executed in order, even if they could have been executed in a different order without having any different effect. So it loses some potential parallelism and optimize, right? I mean, if my next instruction could be executed, but this instruction is waiting for some I/O, I'm kind of stuck. Whereas out of order can race ahead while one instruction is gone. So great. Okay, the pipeline is a lot deeper, and again, the deeper the pipeline, typically I'm able to get better performance. There is a single queue, single shared queue for all execution units. Multiple queues here, what other things, right? 2 instructions can be processed per clock cycle versus 3 instructions. Point is, A15 is microarchitecturally a more powerful thing, so you would expect it to excel at bulk thing, but all that stuff is coming at a cost, presumably of a higher baseline power. Okay, and so if I'm going to get a Porsche and use it, I don't have a Porsche, just using it. Okay, so I'm using it for going to the local grocery store. That's a misuse of the car, right? I mean, so the point is that you should use a processor or a resource for its optimized performance level. Okay, so A7, A15 are kind of examples in a processor context like this. And then the question really becomes one of how do we run the system to make use of these two processors whose operating curves look like in this figure, right? I mean, they're sitting in different space of power versus performance, and my overall system now straddles these. So kind of the idea is, if you look at these two collectively, now I have a more energy proportional system, right? I mean, the big guy had a higher baseline, right? So if I had a very low workload, the big guy would operate at its lowest operating point, but I'm going to be wasting a lot of power. Whereas, so I can lower the performance, but still, whereas a little guy lets me get there. So the idea being that at appropriate times, you transition little guy and that. So the job of this is typically handled by the operating system, although again, Linux, also is a developer in Android, you can do it at the application level. You can pin an application to a particular core. You can fix the frequency. You can play all sort of games there. Of course, with ramifications, right? I mean, on iOS, usually, like I said, philosophically, Apple's strategy is OS has the best global view, and they kind of do things there, and they do an excellent job. I mean, when it comes to power efficiency, I think nothing beats iPhones currently. So yeah, it's a tricky story, but sort of if you look at what can be done, you can imagine lots of approaches, right? One possibility could be I can look at the load on the CPUs on the cores in recent times, and then based upon that, make some decisions. Maybe I know something. Maybe the application gives me a hint saying, I know the network packets are arriving every 10 seconds, so I can arrange for that apply. Right? So there's a mix of prior knowledge, application-specific knowledge, versus what the OS is learning by observation. Right? I mean, maybe the OS after a short while will say, oh, you know, that packet on that connection is coming every 1 second, so it can just optimize for that. So the good strategy would be, or what a pain-free strategy would be, if the system learns, right? And this is where people are using online learning, reinforcement learning, all these kind of methods. But the other philosophically valid strategy is, you know, applications have more knowledge. Let the OS guide, let the applications guide the process. So I'm going to stop out here a few minutes early. I'm not at the stopping point, but there is a lot of stuff happening in this topic, and ripe for sort of exploring some interesting projects. Okay, on this power side. So anyway, so I'm going to have office hours today from 4:30 to 5:30 in my office. So these are in-person office hours.